Hello, my name is Parbrook. I'm Professor of Nitride Materials at Tyndall, and I'm here to introduce the new MOVP reactor that we have just installed. We're using this reactor for the growth of gallium nitride, aluminium nitride, indium nitride, so-called 3-nitride semiconductor materials. MOVP stands for metal organic vapor phase epitaxy, and what we do is we start with a wafer of sapphire, and we then grow on top of that layers of gallium nitride and the other compounds to make our semiconductor device. What I'm going to do is I'll show you how we do that and give you a brief outline of some of the applications we can use. This is the reactor we use for the MOVPE growth. The top part here, where I'm using my tweezers to point, is the shower head. It's got a lot of small holes in it which inject the gas from the metal organic sources and from the ammonia bottle into the reactor chamber. Half the holes introduce the ammonia gas we use, and half introduce the metal organics which contain gallium, aluminium and indium. We also have dopants which come in through the same holes. The lower half here contains 3 wafers, and this will rotate during growth. I can show it rotating now. You can see it there. This increases the uniformity of the wafer. If you look carefully at the shower head up to the top, you can see some larger holes. Those are for optically monitoring what is happening during the growth. This is the reactor closed. The MOVPE growth requires us to grow very, very thin layers. We grow quantum wells that are extremely thin, of the order of 2 or 3 nanometers. That is about the order of 10 atomic layers. That is the typical width of an indium gallium nitride quantum well. MOVPE requires a high degree of growth control. For that purpose, we have a variety of optical monitoring tools to help us see how the growth is progressing in real time. We have here an optical monitor which fires a laser onto the sample and looks at the reflectivity. Oscillations with time tell us how thick layers are. That can be seen on the screen behind you on the right hand side, where you see the red trace showing the oscillations during growth. The rather wider oscillations at the right are due to the growth of indium gallium nitride. The blue trace is using a blue laser which is absorbing at these temperatures, and those shows a roughness measure of the wafer as we grow the initial gallium nitride on the sapphire, as the material has to smooth out slowly during the initial growth to remove the dislocations. On the left hand side you see a circle which is an image of the susceptor as we grow. This is a temperature map of the susceptor at a particular instance in time. That temperature map allows us to control the temperature for the indium containing compounds and ensure it is uniform, as indium containing materials are very, very sensitive to the temperature at which they are growing. You can see the temperature monitoring tool here in the reactor in the box marked Argus. There's also scope for additional optical monitoring which we plan to get in the future. Coming back to the tool here, you may notice the cabinet is quite long. The far end of the cabinet contains all the plumbing effectively to control the gas flows to the reactor. That means we need to have very strict control over the flow rates and the temperatures at which the gases flow into the reactor at, in order to maintain our high quality. Using that, we can grow wafers such as the following. This is a wafer of silicon doped gallium nitride, which is N-type. As you can see, it is a sapphire wafer and you can hardly see anything on the surface because the layer is smooth on the top. If you were to look very, very carefully, you would actually see interference fringes due to the thickness variation. These are actually very, very small, as this reactor is designed for very high uniformity. When we grow indium containing materials, there's some absorption, and you can actually see there's a yellow tint to the layer due to the high indium content. This is a sample which would emit green light if we were to apply a laser, to shine a laser upon it. The applications of gallium nitride are mainly twofold. Initially, the first application is for optoelectronic devices, and these are some commercial LEDs, light-emitting diodes, that are manufactured from gallium nitride, emitting in the blue and the green. There's additional ones in between, and it's cyan. You can use gallium nitride to grow any colour of LED, from the ultraviolet through to the green. People also would like to try to achieve better quality yellow light, although that is very challenging due to the amount of indium that is to be put in. This is a key area of research that we wish to examine at Tyndall. A further area we wish to examine is in the production of ultraviolet LEDs, which have applications for medical purposes and scientific purposes. The most famous application is if you take a blue LED, you can actually use it to make white light. This is the main driver to replace tungsten bulbs, and you can see here effectively the equivalent of a torch. If you had a series of these white light high brightness LEDs together, you would actually be able to manufacture a replacement for a fluorescent tube or a tungsten bulb. The issues is getting the cost per unit down to a reasonable level and controlling the colour temperature and colour quality. This shows an image of some of the other applications. Firstly, we can make a laser. Commonly, gallium nitride lasers are most well known for being used as the enabling technology for a Blu-ray disc drive. In a Blu-ray disc drive, you have a 405 nanometer laser, which provides the read head for the optical pits on the disc that provide the movie or computer information. This shows a laser that I made in a previous place, which shows strong laser emission around 420 nanometers. Another application of gallium nitride is for the use in electronic devices. If you look at this chart, this shows the power of a transistor, or the power density a transistor can hold in a sense, against the frequency of operation. As you can see, silicon germanium, gallium arsenide and indium phosphide all form a line beyond which it is difficult to exceed. However, using wider bandgap materials such as gallium nitride allow you to push up into higher power densities with higher frequencies. This has application for high frequency communication systems, and also more recently people are examining this for high power electronic devices, pushing into this space. There are advantages to operating high power transistors at higher frequencies, as this reduces the size of the capacitors you require, for example. This shows you a typical gallium nitride electronic device. We basically form a source and a drain contact on the surface, which are ohmic, and we put a gate in between. There's a thin layer of aluminium gallium nitride on top of a gallium nitride layer, which is on the sapphire, silicon carbide or silicon substrate. We can choose the substrate according to the application. They each have merits for different applications. At the interface between the aluminium gallium nitride and gallium nitride, we form a two-dimensional electronic gas, so-called. This allows us to have a channel that allows conduction between the source and drain. Applying a voltage to the gate allows the channel to be depleted, allowing us to get a transistor characteristic as shown on this side. These show the two key applications for gallium nitride in electronic and optoelectronics. There are additional applications that one can consider in making MEMS devices using gallium nitride and with selective etching, and also for photodetectors, which is an area of personal interest. I hope that gives a good summary of the facility we have today.